All right, let's get started. I apologize for the very significant delay. I'm just giving up on technology today because it's not really working for me. It's like I hooked everything up the exact same as I have been, and then, yeah. Okay, so obviously I have not graded your exam 1 yet, and I'm still working to get your homework number 4 graded. So I'll get back to you. However, I do have homework 5 for you. I mentioned a while back that this homework assignment will not in any way, shape, or form be on an exam, okay? It's not on an exam because this is just sort of the leftover beam topics that we have yet to discuss. And the problem is if I put it on the second exam, that would just be more beam stuff. And I'm really a big fan of I'm testing you on something and then we move on, okay? So I don't really think that adding more beam stuff to the second exam makes sense. So we had our first exam on beams, on bending, I should say, and so we're going to move on. And so homework 5 will not be on the second exam. It will not be on there. But I'm still going to have a homework 5, and it's due on the 13th, okay? So you've got plenty of time to do it. And with that, I'm just going to sort of shut up and get back into our notes. Now, let me see if I can remember where we left off. Let's just sort of start here. It's been a while since we've talked about stuff in here because we had an exam review, and then we had what I would call a celebration. What I would call a celebration. And you're looking at me with these eyes that it's like you're wondering where I parked in the parking lot so you can slash my tires. What's that? I'm not getting home today. Is that what it is? Uber. Okay. All right. Okay. So let me sort of recap. I want to make sure that everybody remembers what we were talking about before the exam. So we were talking about flanged sections. So that means a T-beam or an L-beam. And so what that means is whenever you have a beam and a slab that's cast monolithically such that you can count a portion of that slab effective in transferring load to the beam. And so one of the things that we have to determine is how much of that slab is effective in transferring load to the beam. And that's the effective flange width. That's a pretty easy calc according to the spec because it's just so much, there's 3 different quantities for T-beams, 3 different quantities for L-beams, and you just compute the minimum. So for T-beams, that's really what I'm going to focus on in here because it really doesn't matter. The only difference is this formula. This is the only difference between the design of a T-beam and the design of an L-beam. We have the minimum of either L over 4, the girder spacing, or this quantity BW plus 16 times the thickness of the flange. Calculate those 3, whichever one is the smallest is the one that governs. The big thing is just make sure that you're cognizant of your units in this calculation because the span length might be in feet, but the web width and the flange thickness are probably going to be in inches, so just make sure that you're cognizant of that. The real complication from an analysis perspective and really from a design perspective is whether or not we're dealing with a rectangular T-beam or whether or not we're dealing with a true T-beam. And so when we're dealing with a true T-beam, the stress block is actually shaped like a T, whereas with a rectangular T-beam, the stress block is just rectangular. If you have a rectangular T-beam, then the analysis is easy. It's just ASFYD minus A over 2. If you're dealing with a true T-beam, there's a little bit more going on, and you sort of have to account for that. So here's the 2 examples that we did in class. This was example 9A and example 9B. Example 9A ended up being a rectangular T-beam. Example 9B ended up being a true T-beam. And those were analysis problems, but we really need to talk about design. And so let's just sort of go through this in a pretty straightforward fashion. First off, when we're talking about T-beam design, we are talking about the design of a known cross-section. We know what the beam looks like. And really, the short answer as to why is because if you can design a beam and you can design a slab, well then just design them separately. And when you put them together, there's your T-beam. So there's really never a situation where the design of a T-beam would be an unknown cross-section. That really wouldn't happen because you can design each component separately. So when you're designing a T-beam, always the big challenge is to select the amount of reinforcement necessary. Now the main complication is to figure out whether or not it's a rectangular T-beam or whether or not it's a true T-beam. So let me show you how we do that. So I want to show you mathematically a way that we can express what a rectangular T-beam or a true T-beam is, and that's by looking at these bullets here. So if I have this T-beam over here, remember H sub F, that is the flange thickness, okay? Now what's A? Now what it means, what A is the depth of the stress block. It's from the top of the beam to the bottom of where that stress block is. So there's really two different cases that we can define mathematically. If we have a rectangular T-beam, that means that A is less than or equal to our flange thickness. If it's greater than our flange thickness, that means we're dealing with a true T-beam. So when we're in design mode, we really don't know whether or not that's the case, because in design mode, we don't know what's going on with equilibrium because we don't know what the steel pattern is. The whole point of design is to figure out the steel pattern. And if you don't know what the steel pattern is, figuring out whether or not you have a true T-beam or a rectangular T-beam is a little bit on the tricky side. So here's what we're going to do. We're going to start off by assuming that it is a rectangular T-beam. Okay, we're just going to make that assumption right off the bat. All right. Now remember, we're dealing with a known cross-section. So if we assume it's rectangular, the first thing that we should be able to do is compute this, rho required. That should be simple. Okay. If the section is rectangular, now recall, if the section is rectangular, that means that A is less than or equal to HF. So here's what we're going to do. We're going to start off by computing a rho required. Remember, what is rho? Rho is a reinforcement ratio. It tells us how much rebar is in the beam as a function of how much concrete is in the beam. So once we know rho, we sort of know how much steel we're putting in there. So we're going to compute rho, and then we're going to say, well, using that rho value, let's back calculate what A is. And how do I do that? Well, what is the area of steel? Well, it's rho BD. And so you should recognize this formula in the middle. A equals ASFY over 0.85 FC prime B. Just replace the area of steel with this, okay? So we'll replace the area of steel, and if you look at that formula, the B's cancel. See how you have a B up top and a B down below, so we come up with this. And so this formula is going to be kind of powerful in our design mode, because what we're going to do is this. We're going to use this formula on the previous slide to calculate a rho value. Then we're going to take that rho value, and we're going to plug it into that. And so what we're doing is we're saying this. We're assuming that the beam is rectangular, then we compute rho. And we take that rho and we plug it into here to compute A. And so depending upon what that A value is, it'll tell us whether or not the beam is rectangular. So we're making an assumption and we're immediately verifying it. Now if the beam is rectangular, then we're good. We just use rho BD, pick a steel pattern, and move on. But if not, if that assumption is incorrect and we're dealing with a true T-beam, then we got a little bit more math to do. So what do? You remember from our analysis example, remember how we took the, remember how we took a T-beam and we split it up like this and this? Y'all remember that? So we had the flange couple and the web couple. Y'all remember that? So here was how we split this up. We basically said that the nominal moment capacity of this section is the nominal moment capacity of the flange couple plus the nominal moment capacity of the web couple, and then we have to adjust everything by our resistance factor phi at the end. Well, let's take a look at these. So we can take these sections, these two couples, and we can sort of break them down. When we break them down, what we'll find is this. One of them is going to be dependent on A. One of them isn't. This is actually a typo. I'm sorry. It says we'll design the flange steel couple first since it's dependent on A. It's because it's not dependent on A. I'm sorry. That's a typo. It's supposed to be because it's not dependent on A. So we'll define the flange steel couple first because it's not dependent on A, and then we'll sort of solve for how much we need in the remainder. So let's go back to this. Does everybody remember this? These were the formulas that we derived to determine the nominal moment capacity of each couple. So the upper one is the nominal moment capacity of the flange couple. The lower one is the nominal moment capacity of the web couple. So we did this in our last example. I know it's been a while, but does everybody kind of remember that? We had a force, and then we had a moment arm. So the force here was 0.85 FC prime times that thickness times that total width, and that total width was B minus BW, so that's how we got that. And then the moment arm was D minus half the flange height. And then for the web couple, it was 0.85 FC prime times that area times the distance of D minus A over 2. Y'all remember that? Is everybody okay with that? Because I know I'm just throwing that at you, but we did that together in our 9B example. Okay? So what we'll do is if we find out we're dealing with a true T-beam, we can calculate this right off the bat because this is not dependent upon the steel at all. This one is, however, because it's dependent on A. So what we'll do is we'll calculate MNF, and then we'll solve for how much MNW we need. For each of those couples, we'll back calculate how much steel we need because, remember, equilibrium has to hold, right? Compression has to equal tension. So for each of those moment capacities, there's going to be an area of steel required to meet equilibrium. So for this first one, you know, this is a compressive force. How much tension force do we need? This is a compressive force. How much tension do we need? And so determining how much tension we need, we can determine the area that we need and just add those areas up and pick a steel pattern accordingly. So for the flange steel couple, it's a pretty simple calculation. C equals T. So 0.85 FC prime times that area has to equal the area of steel times Fy. Just solve for the area of steel. And for the web steel couple, all we have to do is just determine the nominal moment capacity of the web and then back calculate accordingly. So I know I threw a lot out at you. Let's break it down and sort of develop a procedure. So step one, anytime you're doing a beam design problem, the first thing that you'll kind of need to do is determine your moments. Now, if you have a cross-section that's known, you don't need to assume the self-weight. So once you determine your moments, they should be good. The second thing that you'll need to do is assume that phi is 0.9. So you do that and compute Mn. Now what we're doing, this step 3, I really want to make sure everybody's paying attention to this. We assume that the neutral axis is in the flange. So we assume that, we compute a rho required, and then we take that rho and we plug it into step 4 to determine A. So if A is less than the flange height, that means that that assumption that it's a rectangular T-beam is true. And if it's true, we go on to step 5. If not, if we're wrong, well, we skip ahead and we go on to step 8. So step 5 is if we're dealing with a rectangular T-beam, and if we have a rectangular T-beam, we just say rho BD, choose a steel pattern, and verify our assumptions. It's pretty simple. If we've got a true T-beam, we got a little bit more going on. So what we do for a true T-beam is we say, okay, let's compute the area of steel required for the flange couple, compute the moment capacity for the flange couple, back calculate how much we need for the web couple, calculate the area of steel required, and add them up. Now, how am I doing this true T-beam? I'm just calculating a rho and doing rho BD. Remember, it's a known cross-section. The only thing to pay attention to in this calculation right here, I am calculating a reinforcement ratio, but this is a reinforcement ratio required for the web. So the one thing to note is right here. This isn't B, that's BW. That's not a typo, that is correct. So because you're trying to determine how much reinforcement is required for the web steel couple, and the web steel couple looks like this, so we need that width, that B sub W on the bottom right. Rho BD, add them up, choose a pattern. Any questions? I know that's a lot. Don't worry, we'll practice it. Okay. All right, so I have here the following system. Now, just so you're aware, what's going on the slide, I have a diagram on the bottom, and then I have this box up here. I did that because this text is tiny, and so I wanted to make sure that you could read it. So we're going to design a T-beam system, or the T-beam as shown. So let's just take a look at this. We have a beam that's 20 foot long. We have a 1 kip per foot dead load. Now that's superimposed, okay? So because that's superimposed, that means that, excuse me, because that's superimposed, that means that that's on top of the beam self-weight. We have a live load that's 2 kips per foot. We have a 4 KSI concrete, 6 KSI steel. And as for the parameters of the system, the girder spacing is 10 feet. The web width is 12 inches. The flange height is 4 inches. It's got a height of 21 inches and an effective depth of 18 inches. So everybody good on that? Okay. All right. So first off, let me try and clean this mess up got going on over here. Okay. All right. I'm lazy, so I'm going to squinch that up a bit. All right. Okay. All right. So one of the first things that we're going to need to do, and I'm just going to go ahead and get this out of the way now, we're going to have to compute factored moments. Okay. Now here's, I don't know the best way of saying this without sort of annoying you a little bit, but one of the things that we're going to sort of have to do right off the bat is we're going to have to determine some loads and some MUs, okay? And this is where I think you're going to get bugged. First off, let's go ahead and compute a B value. And so this is the minimum of L over 4 BW plus 16 times your flange height or the girder spacing, right? Is everybody with me on this? Okay, and so this is the minimum of what was BW? 12 inches plus 16 times 4 inches. The girder spacing is 10, and this is 20 over 40. Anybody have a problem with that? What's the problem with that? There we go, units. That's what I'm talking about. So this is 10 feet. But we need to multiply that by 12 inches per foot. And this is 20 feet times 12 inches per foot. Okay, and so I'm telling you, on an exam, take your pencil, write the little I, write the little N, put the dot on top of that I, F, T, cross your T's, dot your I's. Seriously, because a lot of folks, I'm telling you, the one thing that trips everybody up on every exam that I've ever given, ever in the history of ever, is units, every time. All right? So on the bottom, that's 120 inches. That's 20 times 12, 240 divided by 4 is 60 inches. And what's that middle one? I'm not that good. Or 16 times 4, 64, was that 76? And so this is 60 inches. Okay, is everybody with me on that? Now, here's something that I think is going to bug you a little bit, okay? Remember, there is a difference between the effective flange width for resistance and how much of this girder we need to consider for loads, okay? In other words, What is the tributary width for this beam? What's the tributary width? 10 feet. So the tributary width is 10 feet, or 120 inches, right? But what we have found is that B is 60 inches, or 5 feet, okay? So here's what that means. When we're trying to determine how strong this beam is, we consider the 60, the 5 feet, because that's all we could consider that's effective in transferring load to that T-beam. In other words, when we're idealizing that as just a single T-beam, that width is 5 feet. However, that T-beam has to hold up not only its own self-weight, but that slab hanging over all the way over here. Does that make sense? So that's where you gotta be careful as to what's going on. So here's sort of what I'm getting at. How do we compute the self-weight of this beam? Like, how do we do that? Well, how do we compute the self-weight of any beam? We take the unit weight times what? Oh. Now, somebody said BH. Now, BH is true if you're talking about a rectangular beam. This isn't rectangular. This is a T-beam, right? So here's what I propose. When we compute the self-weight, we're going to take gamma times the area, okay? But the area, we're going to have to be a little careful with that. What is the area that we're going to have to consider? Well, the area that we're going to have to consider is not only that shaded red region, but all of this as well. Because that T-beam's got to hold that up as well, right? Halfway over to the next beam. Because this T-beam has got to hold up all of this. So I propose that that area is going to be the tributary width times the flange height plus that. Does everybody see how I did that? This is the width times the thickness. This, the width times that height, h minus hf. Is everybody okay with that? All right. Now, let's plug and chug. Again, take the pen, write the units out. Oh, sorry. Does anybody have a problem with that? This is in cubic feet. This is in, what are the units inside this bracket going to be? Square inches. So I need to convert that to square feet. How do I convert square inches to square feet? I want square feet. I have square inches. Well, 144 square inches is 1 square feet. So what does that come out to be? What is this? Oh, a course schedule for statics. And so what does that come out to be? $712.5 what? pound per foot, or 0.713 kip per foot. Is everybody okay with that? So what do I do with that number? You tell me. Somebody tell me what to do. So we add it to the dead load, but ultimately what are we trying to do? There we go. So I need to compute a factored load. So I'm going to say 1.2 times that plus 1.6 times that, right? And so that's 1.2 times that, bless you, plus 1.6 that. And so what does that equal? $5.2 what? And what do we then do with that? And what do I do? There we go. It's a simply supported beam with a uniformly distributed load. Yeah. Yeah. This is a beam, and so we can take that beam, and it can be, that. It can be that. We can put, the beam can be overhanging, and so, it can be anything. Whoa. No. Ask that again. No, the shape of the beam does not affect the structural analysis. The only thing that the shape of the beam would affect is the moment of inertia. Remember when we calculate deflections, like how do we calculate deflections? We need the moment of inertia, we need E, and we need I. And so I changes depending upon what the beam looks like. But it doesn't affect the moments really at all, unless it's indeterminate. But an indeterminate beam, the I changes what the response is. So, but we're not doing indeterminate right now, so we don't need to worry about that. And so what does this come out to be? Remember, 262.5 foot kips. Foot kips. Okay. Are there any questions about that? Is everybody okay with that? Okay. All right. So here's what we're going to do. We're going to continue assuming, so we've got MU. What's the second step, regardless of whether or not it's rectangular or T? MN. So let's continue that. And remember, to do this, we're assuming phi is 0.9. So now what was that? Did you say 262.5? What does that equal? Have a second on that? Yep. Now, You know by now that whenever you're in design mode, we might as well go ahead and convert that to inch kips. So what is that in inch kips? Everybody's all quiet. $3,500 even? All right, we'll just do 3,500. Okay. All right. Here's the thing. So step 3, what is step 3? We compute what? All right, so we compute row. Compute row required, but we're assuming a rectangular T-beam. So we're assuming a rectangular T-beam, but we're going to verify that assumption later. Now let's see what it comes out. Let's see what happens. So row required, and this is a big formula, okay? Okay. This was, what was this? What was FC prime and FY? And this one was 60? Right. Remember, 1 minus and 1 minus. 0.85 for KSI. Now, your B. We are assuming that this is a rectangular beam. So when we use B, we use the whole width. Okay? So this is the 60 inches that we computed, the effective flange width. And this is D, which is 18 inches, and that's squared. And so right now you should see why we converted the MN to inch kips, because this is KSI, inches, so that needs to be an inch kip, so everything's copacetic. Now, what do we get for this? Now, I want everybody who's got a calculator, your engineering students, you should have your Casio FX115 ES Plus with you at all times. I want everybody to tell me what they're getting for this. Remember, this is a big formula, so I want to sort of make sure that everybody's got the accurate answer here. What was that? Okay, all right. That is correct. Now, here's where things change. What we would have done before, if it was a known cross-section, is we'd have just said row BD, plug it in, and we're good. And we might be able to do that. But we have to do a little bit of a verification. Sorry. We got to back calculate A. So here's what we're doing. Step 3, we made an assumption that this was a rectangular T-beam, okay? And so we compute the row value assuming it's a rectangular T-beam. Now what we're going to do is we're going to take that row value and we're going to back calculate A to see what A would be if we used that much steel. And so let's see what that is. Okay, and so that A value is rho FYD over 0.85 FC prime. And remember, that's just ASFY over 0.85 FC prime B, and just plugging in the definition of rho. So what is that? 0.978. Now, what are the units? Inches. Do I have a second on that value? Okay, now, what does that mean? So, step 3, we assumed that this was a rectangular T-beam. Was that assumption accurate? Yeah, it was. Assumption was accurate. This is a rectangular T-beam. So what we can say is assumption was valid. In other words, A is less than or equal to HF. So it's a rectangular T-beam. Okay. And so if it's a rectangular T-beam, what do? We go to step 5. And what do we do on step 5? We just compute rho BD. So step 5. Remember, use the entire rectangular width. So what's that? Do I have a second on that? All right. And so all we have to do from this point forward is we go to our this, and we find a pattern of steel that will fit inside of our web. How wide is our web? I don't remember. What's the web width on this? 12 inches. So as long as the web is 12 inches wide, we're good. So 3.33. So let's see. What about 8 number 6s? Let's start there. 8 number 6s. Yeah, that doesn't work. 6 number 7s. That doesn't work. 5 number 8s. That doesn't work. How about 4 number 9s? Not quite cutting it. What about 3 number 10s? What about this right here? 3 number 10s. 3 number 10s would work, right? Everybody see that? I don't see any patterns that are smaller than 3 number 10s, right? So I would propose that the answer to this problem is to use 3 number 10s, which has an area of steel of 3.82 square inches, and it fits within our beam because we have a limiting width of 12 inches, and this is 10.34. Now, we still need to verify that phi equals 0.9, but other than that, I think we're good, right? Now, this is a rectangular T-beam design. What we have to do next is a true T-beam design to make sure that we're all understanding what's going on. So spoiler alert, what do you think is going to happen here? True T-beam design. Now, this is what we're going to do on Monday. So I want to show you a couple things with that. First off, as you'll see, this problem, I've simplified a few things for you. I gave you the MU, and I'm telling you that B is 54, so we don't have to go through and compute all those weights. And then what we're going to do afterwards on Monday is we're going to discuss a doubly reinforced beam. And so to give you kind of an idea of what's going on with a doubly reinforced beam, this is what I mean by a doubly reinforced beam. A doubly reinforced beam is when not only do you have steel in tension, but you have steel in compression. So there's a couple things that you'll need to understand. One is how to actually do that analysis. And two, there's a lot of different notation. So we have D primes, we have AS primes, and we have a lot of different strain notations and whatnot that goes along with that. Don't worry, we'll take that one step at a time just as we do this one. But when we come in on Monday, be prepared to do this example, and we'll start getting into doubly reinforced beams. One other thing about doubly reinforced beams, we don't design them. We really just analyze them. So we don't really have to worry about that. So that's all I have. I will see you all in 10 minutes.